Okay, so today we're taking a look at section 6.5, titled Operations with Radical Expressions. And our learning target would be that I can do operations with radical expressions. So basically the same. There's a couple of operations we're going to do. A lot of what we're going to do is simplifying. Actually, I think everything we're doing is simplifying today. But a few different types. So let's start off with the third root of 27 y to the 12th z to the 7th. This isn't terribly different than what we did in the previous section, except that in the previous section, when we were simplifying, everything kind of went away. In this case, not everything is a perfect cube, but some of it is. So let's go ahead and simplify this. So you can think of the 27 separate from the y, separate from the z. Kind of think of them all as their own separate things. Cube root of 27, what would that be? 3. It was a perfect cube. So 3 gets to come out, just a normal 3, a rational 3. It's not an irradical anymore. Think about the y's. What does y become? Y to the 4th, because we would do division. You had a 12 with an index of 3, so you got to divide that. 12 divided by 3 was 4. No remainder there. But look at the z. 7, can we divide it by 4? Well, we can, but there's a remainder, right? How many whole number times can I, deal with it there? I can pull z out twice. 7 divided by 3 would be 2, but there's a remainder. So the whole number piece is 2, so I get to pull z out. But then whatever is the remainder, whatever didn't get to come out, is stuck inside. And it's still a third root. That doesn't change. It doesn't become a square root all of a sudden, so you have to keep the index the same, still a 3. And what's left inside of that cube root? How many z's? Just a single z. If I had z to the 6th, that's what we dealt with here, but it was z to the 7th, so there's one z left inside that radical. So here's your answer. We could do a couple more of those, but there's some fractions that I want to spend a little bit more time on. So we're going to jump into one of those. Let's deal with the cube root of 2 over 9x. There are a few rules about simplifying that we need to be aware of. One is that you cannot have a fraction inside of a radical. So the first thing I'm going to do is I'm going to deal with that. Since I have a fraction there, I'm just going to split it apart and think of the numerator and denominator separately. So the numerator is the cube root of 2. The denominator is the cube root of 9x. So that's one rule about simplifying. You can't have a fraction in there. But another rule is that you are not allowed to have a radical in your denominator. We already dealt with it before when we did imaginaries. You couldn't have an I in the denominator for the same reason. But no radicals in our denominator. So, third root of 9x. 9 is not a perfect cube. X is not a perfect cube. I can't just simplify it. So we do what's called rationalizing. Right now our denominator is irrational because there's that root there. I need to get rid of it, so I need to turn it into a rational number. So I have to rationalize it. So we do that through multiplication. But it may be helpful first, and I think it is helpful first, for us to think of that 9 as a power of something smaller. Isn't that 9? Couldn't I think of that as 3 squared? That will make the problem easier. We'll deal with smaller numbers, and if I think of it as a 3 squared 9 or 3 squared now, I will have less simplifying to do later. So Very important if you can write it as a power to do so. I don't care about the numerator. I'm talking specifically about the denominator. So now I can rationalize through multiplying. Because it was a cube root, I have to multiply it by a cube root. My goal after the multiplication is to eliminate the cube root. And the way we eliminate a cube root is by having a cube of something. So that 3, right now I have 3 squared. I have 2 3s there, but I would like to have 3 of them. So how many more 3s do I need to bring in to the problem? Not 3 more, just a single 3. So I'll have a 3 there. We'll see this more in a second. I think it'll make, if you're confused right now, you'll see it here in a second. But now let's take a look at the x's. Currently I have 1x. And because the index is 3, because it's a cube root, I want 3 x's. I only have 1. How many more do I need? 2. I'll need to bring 2 more in. Now I'll have to do that to the numerator also. So let's go ahead and write that. Let's go ahead and multiply the numerator first. I'm not that concerned about what the numerator ends up being, but I do need to multiply it together. They're both cube roots, so go ahead and multiply the radicands, or the things inside of them. So 2 times 3x squared becomes 6x squared. And look at the bottom. I had a 3 squared and I multiplied it by another 3. 3 squared times 3 is 3 cubed, or 3 to the third power. Normally I would like to write that as 27, but because of what I'm going to do next, I'm going to leave it as a power, so 3 to the third. And then I had x times x to the second. X times x to the second is x to the third. So now if we focus just on that denominator and simplify it, we have a third root of 3 to the third and a third root of x to the third. When I simplify that, what do I get? Just a 3 and an x, because the cube root canceled out all the cubes. So I just got 3x. You're trying to get rid of the root. Yep, I'm trying to make it not an irrational number. Trying to make it rational. When you look at this problem, you might see a 6 and a 3 and say, oh, I want to simplify that, but you can't. The reason being, 3 is a rational 3. It's not in a root. The 6 is in a cube root. They're not the same type of numbers. You can't simplify those. Same thing with the x's. We learned before that, hey, if there's x's on the top and the bottom, I need to combine them together. So that might seem like, oh, I need to fix this, except we know that if I fix it, then I have a radical in the denominator, and that's not allowed. So the fact that I can't have a radical in the denominator supersedes the fact that there's x's in the top and the bottom. So this is your answer. That's simplified right there. I definitely think the fractions are the trickiest part of this section, and there's 2 types of fractions we'll deal with. Personally, I think this is the trickier of the 2. Let's do another one. Let's try a 5th root of 3 over 4y. So just like the last problem, our first step is going to be to separate the numerator and denominator. They're each going to be roots. Now, actually, while I'm writing the 4 here, how could I rethink of 4? 2 squared. I didn't mean to write that as a third root either. Let me go back a couple steps here. Okay. 5th root of 2 squared y. Now, once again, the reason I am doing that, if I didn't write that as 2 squared, if I thought of it as 4 to the first, I would need 4 more 4s, which is a lot. If I think of it as 2 to the second, I only need 3 more 2s. That seems a lot easier, a lot smaller. So let's find out what we're missing and multiply it in. And we only focus on the denominator. So yeah, question. Yeah, so if I could, like, let's say that was a 5 instead of a 4, then you would have to think of it as 5 to the first. And so then you would need like 4 more 5s. But if you can write it as a power, if that's possible, do it, just because it makes it smaller numbers to deal with, and you're closer to having your exponent match. Oops, I didn't mean to do it. Your exponent match your index. So I want a total of 5 2s. Right now I have 2, so I need 3 more. Same thing on y's. I have 1 y, therefore I need 4 more. So in the numerator, I have the same thing that I'm multiplying in. However, I'm not trying to eliminate the radical in the numerator. So in the numerator, there's really no point in me writing it as 2 to the third. So I would rather not write it as 2 to the third. I'm going to have to multiply it by the 3. So I would like to think about what 2 to the third is. 2 times 2 times 2 is 8. So understand those are the exact same thing that I'm multiplying to the top and to the bottom. But in the bottom, I was trying to think of it as 5 2s. And in the numerator, I don't care about that. That's why I've written them in a different style. Now, I don't know that I have to write this fifth root there in the bottom, especially as you get more and more practice. If you want to go ahead and write fifth root of 2 to the fifth, y to the fifth, and then simplify it in the next step, you can. Or I'm completely fine with going straight to what the simplified denominator would be. I'm going to have 2 to the fifth, but the fifth root of that is just 2. I'm going to have y to the fifth, and the fifth root of that is just y. That's your denominator. Your numerators, multiply them. Fifth root, 3 times 8 is 24. And then y to the fourth. 24 is a big enough number with enough factors. You might see that and think, can't I simplify that? But the answer is no. If you do a factor tree on 24, you get 2 times 2 times 2 times 3. You have 3 2s and a 3. I don't have 5 of anything. So there's nothing that can pull out there. That's your answer. All right. We have some more simplifying problems, but I'm gonna jump down here. Let's try this problem. 5 square root of 12 plus 2 square roots of 27 minus, not plus, minus the square root of 128. You cannot combine those together as is. You have to think of those square root pieces. Square root of 12, square root of 27, square root of 128, and you can only combine through addition and subtraction if they're the same. And they're all unique here. They're all different. It's kind of like having an X, a Y, and a Z. So we cannot combine those. However, I don't think any of those are simplified. So we can simplify each of those first. Let's start with the square root of 12. How can I break down the square root of 12? Square root of 4 times the square root of 3. Square root of 4 is 2. So in total, I get 10 square roots of 3. And then plus, let's do the next one. 27 breaks down into 9 times 3. Square root of 9 is 3. Square root of 3 does not simplify, so in total there I have 6 square roots of 3. Is that going to be able to combine with 10 square roots of 3? I have 10 square roots of 3, and now I have 6 more of them. Let's go ahead and check the rest of the problem, though. 128. If you recognized that that was 64 times 2, that would be the fastest way to break that one down. But what if you didn't realize that there was a 64? What if you said, oh, well, at least I can do a 4. It'd be 4 and what? 32. Oh, but 32 breaks down. Maybe you say, oh, it's 4 and 8. Oh, and then 8 breaks down, right? We could do that kind of the long way if you want, as long as you find out as many, get it to perfect squares. 2 times 2 times 2, in this case, times square root of 2. 2 times 2 times 2 is 8. So I get 8 square roots of 2. So that's kind of the slower way to do that one. If you had realized right away it was square root of 64 times square root of 2, then you could have got 8 square root of 2 right away. Same answer. Just depends on, I guess, how you break it down. Okay, so now look down there now that I've simplified. Can all of those combine together? No, the last one cannot. It's a square root of 2. We can combine the first two together. I have 16 square roots of 3 minus 8 square roots of 2. That's all you can do on that one. But if we did have a couple of them that went together, so you need to do that. All right, let's jump into the other type of fraction. Four plus the square root of 2 over square root of 2 minus 3. This is unique from the first couple fractions we did because of the plus and the minus there in the denominator. It's not a single term. It's a binomial, if you will. So we have to approach it differently. We are still going to rationalize. We have to multiply by something, but it's a little more complicated, perhaps, that at least a piece that I multiply it by than it was before. We did do this when we had imaginary numbers. We talked about multiplying by the conjugate. That's what we have to use here also. Focus on the denominator. Does anybody remember enough about conjugates to know what the conjugate is for this one? Adam? Square root of 2 plus 3 is correct. That is called the conjugate. It is the exact same thing, except for the sign in the middle. So if I multiply that to the bottom, I have to multiply it to the numerator also. And so now we have two multiplication problems. And the way we multiply those together is by distributing or foiling. So let's do that. First, in the numerator, 4 times the square root of 2. 4 is not in a square root. 2 is. You can't actually multiply them directly together. Instead, I have 4 square root of 2. 4 times 3, well, that's a 12. Then, square root of 2 times square root of 2. becomes just 2. You could have thought of it as, since they're both square roots, you can multiply them together. Square root of 2 times square root of 2 is square root of 4. That simplifies to just 2. And then square root of 2 times 3. Once again, the 3 is not in a square root, so I don't get a 6. Instead, I have 3 square roots of 2. We'll come back to the numerator. Let's go ahead and look at the denominator first. FOIL here. Square root of 2 times square root of 2, 2. Square root of 2 times 3, positive 3 square roots of 2. Negative 3 times the square root of 2 is negative 3 square roots of 2. And then negative 3 times positive 3, that's negative 9. Why is it that we use conjugates? Your positive 3 square root of 2 and your negative 3 square root of 2 cancel each other out. So my denominator is a negative 7. My numerator, I have 4 square roots of 2 and 3 square roots of 2, so that's a total of 7 square roots of 2. And I have 12 plus 2, that's a total of 14. So we got it to a fraction where the denominator is an integer. It's a rational number, so that's great. We don't like a negative denominator, though. But while I deal with the negative, can't I also divide everything by 7? Yes, so I'm going to actually divide everything by a negative 7 to get rid of the negative also. So I get a negative square root of 2. And then 14 divided by negative 7 is negative 2. So I have negative square root of 2 minus 2. You won't always be able to simplify, or you won't always be without a fraction. But in this case, we are. So don't forget about conjugates. All right, that brings us through the notes. You'll need to do some practice, some more practice to be good at it. So I would like you to work on those practice problems on the assignment.